Hello. So welcome to Metallic Minerals in Minnesota. What I'm going to focus on in this video lecture is essentially what the metallic minerals are, the various ways in which they form, and where you're going to find them in Minnesota. We're not going to dive into the ins and outs of whether or not mines should be permitted. That's a very long and very personal conversation. So I'm going to focus on the science. So let's dive in and okay. So how am I going to organize lecture today? First, I'm going to give you an introduction to metallic minerals. Then we're going to look at various ways in which ore is formed and what ore is, with a focus on the metallic minerals that are currently extracted or could potentially be extracted in Minnesota. So that's iron, zinc, copper, nickel, and platinum group elements. And then at the end, we're going to look briefly at some of the environmental impacts of metallic mineral mining. So when we talk about metallic minerals in Minnesota, shift your gaze over to the right here. A lot of people think about banded iron formation. That's this red, black, and white banded layered material that is Precambrian in age. Up here, we're looking at Archean banded iron formation near the Sudan mine. Turns out this rock isn't actually what produces the high-grade ore. What is or was extracted was the hematite-rich material that was effectively concentrated by later metamorphism. And also world famous is taconite. These are the pellets made from low-grade iron ore. So with that brief introduction, let's see what's happening here. All right, so I want you to think back to what you know about metallic minerals. So and rocks and elements. So rocks are made up of minerals, which are the minerals of various combinations of elements. So we've got our minerals here. Now, as you may or may not recall, most of the main rock-forming minerals are silicate minerals, and those are the minerals that use silicate, the silicate tetrahedra, SiO2, as the building block. So that's all our non-metallic minerals. On the other hand, most metallic minerals are either sulfides, that is, they use sulfur as the sort of building block, or oxides, they're structured around oxygen. So that's metallic minerals. Now, metallic minerals can actually be further subdivided into ferrous minerals. That's the minerals that contain iron, and non-ferrous minerals. So you've already looked at galena and you've looked at pyrite, but there's a whole bunch of different minerals once one starts thinking about the metallic minerals. So what are these? Well, there's a lot of them, but I'm going to focus on the ones that are important for Minnesota. So as I mentioned, they either build their mineral around sulfur, and that's all these minerals. So these would be sulfide minerals. And so we have galena, chalcopyrite, sphalerite, molybdenite, which isn't important in Minnesota, pyrite, bornite, arsenopyrite, and stibnite. So these are some examples of common sulfide minerals. Now, let's think about some common oxide minerals. I'll just point out, this is just a list, a reminder of the elements that are of particular interest in Minnesota. So some of the common oxide minerals are hematite or hematite, you can pronounce it either way, magnetite, and limonite. Now, hematite or hematite is it's actually really interesting because it presents in a variety of ways. So if you look down here, we can see 4 samples of hematite. Now, it can be metallic looking, which would be these 2 samples on the lower left and some of the sample on the right. Metallic looking hematite also gets called specular hematite. If it ends up being made up of hematite flakes, being kind of flaky, it gets called micaceous hematite. And then up here, you see your earthy looking hematite. They both produce the same kind of streak on a streak plate. What I've got here on this slide is some of the main ore minerals for copper, zinc, nickel, iron, and lead. So you can look at a mineral formula. Copper is Cu. You can see that all these are minerals containing copper. Oh, and some of them also contain some iron. So there are some TUFAs, if you like. Minerals containing zinc or Zn. You can see that here. A zinc sulfide, here's a zinc carbonate. Nickel, pentlandite is a sulfide. It contains, as well as nickel, which is Ni, it contains some iron, another tufa. Once we get into iron, the list gets a bit longer. Hematite, magnetite, goethite, limonite, and siderite. What I want you to notice here in the formula is there's this little NH2O. That means that it's like goethite, only it's got a bit of water in the formula. That's that dot NH2O. It's sort of, okay, there's a little bit of water in there. And then the minerals of lead, they all have Pb, lead in them. But what you'll notice here is galena, which you're familiar with, is a lead sulfide. But then you get into sulfates and carbonates. And then pyromorphite is a phosphate. So it's far more complicated. But galena is the main mineral containing lead. So you can look at a formula and you can pretty quickly tell from looking at whether or not it has Cu, Zn, Ni, Fe, or Pb in it, whether it's, what it's containing. Okay, so the next question is, what exactly is ore and how it's formed? So a simple definition might be ore is a body of material, in this case, rock, from which one or more valuable substances, in this case, minerals, can be mined at a profit, which you may feel is kind of vague, but this all gets down to the economics of whether it is profitable to extract this material from the earth for use in manufacturing, whatever materials are needed. So the term ore is primarily used for metallic minerals. And one thing that's really important is in rocks, the metallic minerals, or more importantly, the elements they contain that are of interest to us are not normally concentrated enough to be mined at a profit. So what has to have happened to the rocks is somehow some earth processes have to have naturally concentrated the mineral in the rock. And when I say the mineral, yes, we're talking about minerals, but what we're particularly interested in is, okay, does that mineral contain whatever element we're interested in? So ore can be extracted from open pit mines. This is the Hull Rust Mahoning pit in Hibbing, and underground mines. This is an image from the Sudan underground mine, which one can do tours of, but it's now no longer operating as a mine. So we talked about earth processes having naturally concentrated the mineral. The big question now is, well, okay, why or how is ore actually formed? And there are three main processes through which ore forms, and one we're not going to deal with. So magmatic processes, that means something to do with intrusion of igneous rocks. Secondly, hydrothermal processes. So this means hydro, water, thermal, heat. So a process that involves hot fluids, and this can take place in various ways, and we'll be investigating it. And then there are a bunch of non-magmatic geochemical processes. What I've missed off here that could be lumped into non-magmatic is the alteration and weathering of rocks at the surface can, in some cases, concentrate the material, such as the case of the production of aluminum-bearing ore called bauxite. Anyway, let's examine ore formation now. So, first of all, this is a busy slide, but I'm going to talk you through this. So, ore can form from magmatic processes. So, up here, what I'm circling now is a kind of goofy looking magma chamber. So we know we have magma cooling in a magma chamber, molten rock. Now, within that magma chamber, what happens is as minerals and obviously all the elements they contain settle out of the molten material, they can form these layered igneous intrusions. So here you can see some layered igneous rocks. And yes, they do look a bit like sedimentary rocks, but if you look at them with a hand lens, you'll see they're made up of interlocking crystals. And what happens is during this settling process, depending on the composition and conditions in the magma chamber, these layered intrusions can end up hosting mineral deposits. So elements that were in the magma, because of how everything works in the magma chamber, get concentrated in particular horizons. And elements that we find in layered igneous intrusions include copper, nickel, platinum and palladium, in other words, platinum group elements, as well as chromium, titanium, and vanadium. So, layered igneous intrusions. Now, where in Minnesota do we see potential ore deposits associated with magmatic processes? And the answer is in the Duluth complex. So you may or may not recall that the Duluth complex is a intrusive igneous sequence associated with continental rifting in the Proterozoic. So prior to 500 million years ago. in this case, close to 1 billion years ago. So first of all, let's just look at the map in the lower area here. We have a index map. What I want you to notice is Lake Superior is in here. Close to the shore, there's a lot of volcanic material that was the sort of surface expression of what was happening down in the magma chamber. And what we're looking at here is the northern part of the Duluth complex. And there's a whole bunch of intrusions along here. So we're on a map here, and there's a bunch of prospects. Dunker Road Prospect, Babbitt Prospect, and there's Dunker Pit. So if you go up to the top here, this is a cross section. Remember, it's a vertical slice, and it's going from somewhere in the northwest across the boundary of the much older rocks with the Duluth complex. So it's going from northwest to southeast. And what you'll notice is that all the copper, nickel, platinum group element mineralization is associated with the lower portion of the Duluth complex. So what's actually happened here is that, yes, there was likely some concentration of your copper, nickel, platinum group elements, but then later on there was some metamorphism that further concentrated some of those elements. So that's magmatic processes in Minnesota rocks. Now, you remember I introduced hydrothermal processes, so that's water and heat. So first, check over on the left. So just reminding you, this involves fluids associated with magma. So basically, any fluid that has been heated up, it may be fluid that has been produced as a consequence of maybe magma interacting with rocks that contain water, or by magma interacting or heating up seawater. So that happens, and then that hot fluid basically catapults a whole bunch of, or catalyzes a whole bunch of geochemical processes that can precipitate and concentrate mineral deposits. So what's the easiest way to think about it is those hot waters scavenge all those elements from whatever they're moving through, and then they deposit it in, or them in a concentrated way. And this leads to a really important group of mineral deposits. So we use the word deposits for many of these mineralized areas because we're thinking about the minerals as having formed there through quote unquote deposition from fluids. It's not like sedimentary deposits. It's just, okay, there were hot fluids scavenging and then precipitating a whole bunch of minerals in the rocks. So these VMS deposits include copper, lead, zinc, gold, and silver. Now, there is also another group of mineral deposits associated with hydrothermal processes. These are called porphyry deposits, and they're a whole other group. Basically, there's a whole bunch of ore minerals that form within volcanic rocks, and they're associated with hydrothermal alteration. They typically form in felsic igneous rocks. Think back to what you learned about igneous rocks. So that's the background for hydrothermal processes. Now let's move over to two somewhat complex maps. So there are two areas in Minnesota that have the potential for mineralization associated with hydrothermal processes. These are the Archean Greenstone Belt. So the Archean Greenstone Belt is effectively all the rocks shown in the green here. So these are volcano-sedimentary rocks that have been hydrothermally altered. And you can see that kind of outlined in this red area in here. So Archean Greenstone Belt. There are also in areas slightly further to the south, younger rocks, Proterozoic, as opposed to Archean in further to the north. There are volcano-sedimentary rocks that have the potential for carrying volcanic massive sulfide deposits. Now let's think about ores that form from non-magmatic geochemical processes. So these are processes that take place at the near surface or near the land surface, which could be on the seafloor without any contributions from magma or magmatic heat. So we're going through the text first. Now, these processes typically involve some kind of redox reaction, and that is your oxidation and reduction chemistry. And this can be simplified by just thinking of it as being about whether or not oxygen is available and whether it reacts with iron in seawater, causing it to precipitate. So if you think back to early Earth history, oxygen first started being produced by photosynthesizing organisms. And that basically, that event started to produce iron-bearing banded iron formations, often referred to as BIFs, B-I-Fs. So these banded iron formations resulted from the iron in the seawater effectively reacting with the oxygen, which caused iron to be precipitated and deposited on the seafloor. So we start seeing hematite and magnetite. Now, the banded iron formations usually include chert and shale as well. Now, if you move over to the right here, we've got some images. If you go to areas near the Sudan mine, there are some beautiful exposures of banded iron formation. Now, what's interesting, and I've mentioned this before, is this is just, it's total eye candy. But this isn't actually what gets mined. This is left behind because the silvery gray area, yes, that is hematite, may have some magnetite in it, but there's so much jasper and chert in here. The jasper is the red iron-stained quartz-like material, and then the white is actually quartz or chert. So this is not the ore. The ore itself is pure hematite. So we know here, shown in blue, that photosynthetic organisms made oxygen, and that reacted with the iron in seawater to precipitate iron oxide minerals on the seafloor. So up on the upper right, this is the ore associated with Sudan mine, which is a deep underground mine. On the other hand, lower down here, this is a view of the Hull Rust Mahoning mine near Hibbing. And this, excuse me, this is, pardon me, this is an, an, an open pit mine. So we're just going to examine the difference between these two types or areas. So first of all, we're going to look at the Sudan underground mine. So here is an overall map, and some of you will be familiar with the iron ranges in Minnesota. We have the Cuyuna Range or ranges further to the south, then the Mesabi Range, the Vermilion Range, and then way to the northeast, the Gunflint Range. So the Sudan underground mine in Tao Sudan, Minnesota, is located in the Vermilion Range, and it is Minnesota's oldest, deepest, and richest iron mine. So it opened in 1901 and then ultimately closed in 1962. It is an underground mine. It goes down 2,341 feet, and it produced high-grade iron ore. The ore looks like this. It is essentially hematite. These are Archean rocks, and we know how that iron was formed. Think back to non-magnetic ore forming processes that we just looked at. But what also happened in these Archean rocks is that ore or the iron got further concentrated during metamorphism in fault zones. And there's actually 65% iron in these rocks. Now, let's move over to the right here. This diagram is a vertical slice. So here is the land surface. And what this is capturing is, here you've got a legend, and in red is what's called the massive hematite ore. So that's the stuff they want to extract. What you're looking at here, this is the head frame or shaft. So if you visit Sudan Underground Mine and do an underground tour, you go down in the, if you want to call it an elevator, all the way down to this level down here. But what you can see is there are a whole bunch of different levels. So they would extract the ore from these adits, these horizontal tunnels that they built. And they developed a really effective way of extracting the ore and leaving anything they didn't want behind. So this is gives you a visual of what's happening underground to get ore like that. Now, again, we've got a busy slide. Let's work through it. So here we've got that same map. Now we're looking at iron mining on the Mesabi range. So now the biggest Mine is the Hull Rust Mahoning open pit mine, and I showed you an image of that earlier. So first, look at the text on the left. So this is where lower grade iron ore is extracted. So this iron ore was also formed as a consequence of iron initially precipitating on the seafloor, but it had a much lower concentration in general. So it wasn't economic to extract. But what they discovered is that they could concentrate it. So let's just step through a few things. And these points aren't quite in the order I want. So within the rocks here, which are Proterozoic, so they are younger than the Archean banded iron formations of the Sudan mine. The rock unit or formation that you see tracking where this red line is the Biwabik iron formation. Now, let's just move over to the right here. So, up at the very top, there is a map. North is to the towards the upper right here. And you can see all these pink dots, basically, pink splotches. And note this kind of little bend in everything. So what we've got here is a more detailed information about what's happening on the Mesabi Range. And the pink areas show areas where this low-grade iron ore has been extracted. Down here, what it's capturing is the overall layering within this Biwabik iron formation. And this is quite confusing, but essentially there are a bunch of different layers and they get the creatively named units: lower cherty, lower slaty, upper cherty, upper slaty. So this is a from a research publication. I wanted you to get a sense that yes, we're dealing with sedimentary layers, and yes, it is complex. So this is capturing the Biwabik iron formation, which is Proterozoic in age. Now, within the Biwabik, there are some natural ores. And this is the phrase that gets used for areas where iron is more concentrated, and that would be 51 to 57% iron. However, for the most part, the most iron that is found in the Biwabik formation is somewhere between 30 and 35%. And it's in the form of magnetite. There's some iron silicate minerals and then iron-bearing carbonate minerals. Now, this rock gets called taconite, or more specifically, the pellets that are made from it basically they're made to concentrate the iron, because this area is not economic to mine or ship the ore from if it only contains 30 to 35% iron. So they extract the rock, they process it, and they form these taconite pellets. And in these pellets, one finds 60 to 70% iron. And so that's what makes mining on the Mesabi Range economically feasible, production of the taconite. Okay, so environmental impacts of metallic mineral mining. So there are all the economic advantages of mining, what that does for jobs, etc., and maintaining communities. What we're going to focus on here is the environmental concerns. So water pollution, air pollution, land degradation, erosion, loss of biodiversity, habitat damage, and greenhouse gas emissions. And the graphic here captures the potential adverse impacts of mining. Now, the details here depend on the type of mining, open pit, underground, chemicals used, size of the mine, and the environmental practices that get adopted. What we're going to focus on is acid mine drainage. So, what exactly is acid mine drainage? So, focus over here on the left first. So, if we have rocks that contain sulfur-bearing minerals, and think back to the minerals that we're interested in, a lot of them are sulfides. If these rocks containing sulfur-bearing minerals are exposed to air and water, they can react to create sulfuric acid. And that sulfuric acid will effectively change the acidity of the water. So natural waters or roughly neutral water ranges between 6.5 to having a pH of 8.5, whereas acid mine drainage ranges from a pH of 2 to maybe 6, and sometimes lower than a pH of 2. So that's your sulfuric acid. Now, it doesn't stop there. What happens is that the sulfuric acid in the water will typically dissolve, or you can think of it as scavenging or picking up toxic metals from the rocks. So sulfuric acid interacts with the rocks and picks up copper, aluminum, cadmium, arsenic, lead, mercury from rocks that it moves across or through. And a reminder, this process can take place underground or at the surface, as long as there's some air and water. So what that means is that the water will now be not only acidic, but it will be carrying a whole bunch of dissolved elements that may be toxic. Now, when there are the concentration of these is high enough, one ends up with a orange, yellow, red slime that is called yellow boy. It's made up of these metals, and it precipitates or coats the stream bed. So here you can see some of that acid mine drainage impacting a surface stream. Now, can we try to mediate this? Yes. One of the multitude of ways is by using limestones and some other rock to try and have chemical reactions to extract some of these contaminants and reduce the acidity. The graphic here tries to capture what's happening during the development of acid mine drainage. So we have our oxygen and water and sulfide minerals producing sulfuric acid. This can happen in open pit mine or in an underground mine. So, and there might be underground groundwater, and here you can see groundwater moving, reaching the surface. And this has a huge impact on the health of the stream and the health of anything that uses the stream. So that's our concerns about acid mine drainage. Okay. So thank you very much. And that's it for now. Bye.